Okay, let's unpack this. Today we are getting into some seriously high-stakes territory in pharmaceutical research. We're talking about structure-based drug design, or SBDD. This is the incredibly complex process of creating new drugs, these tiny molecules that have to fit perfectly into a protein pocket. It's chemistry, biology, and a whole lot of AI.
Oh, SBDD is absolutely the frontier. And the complexity, it wasn't just in the chemistry. Historically, it was in the software, the computational
How
tools.
so?
Well, everything was siloed. You'd have one specialized algorithm for, say, dreaming up a brand new molecule, and then you'd have a totally different, highly optimized piece of software just for checking if a molecule you already have fits into that pocket.
Right, two separate jobs, two separate tools. Well, our source material today introduces a model that's trying to just blow all that up. It's called OMTRA. And you can probably guess the researchers have a bit of a sense of humor because it stands for one model to rule them all.
It's a fittingly ambitious name, I gotta say. The mission here is huge. They want to create a single, unified AI framework that can do all of these different SBDD tasks, from discovery to fitting. All of it.
All in one place.
And this is the key. Deliver state-of-the-art performance in every single one.
Yeah.
They basically want one model to replace an entire software pipeline.
And I guess the real hook is that flexibility, handling things that used to need their own special software, like de novo design, which is inventing something new.
Right, truly from scratch.
And molecular docking, which is just seeing how an existing drug fits.
Exactly. And to really get how OMTRA does this, we have to look at those two generative challenges it's trying to
Yeah.
synthesize.
Okay, so the first one is structure prediction, docking.
Mm-hmm.
You've got a molecule you already know, and you're just trying to find its best 3D position, its pose inside that protein pocket.
It's a prediction problem, pure and simple. And the old way of doing this involved these really slow, intensive search algorithms that would test millions of possibilities.
Just brute forcing it.
Pretty much. And then there's the second approach, which is the really creative one, de novo design.
This isn't just moving a puzzle piece around.
Not at all. This is where the model is actually generating the identity of a brand new molecule and its 3D structure, all based on the protein it needs to bind to. You're basically inventing a new key for a specific lock.
So you have pose prediction on one side and total molecular invention on the other. And for a long time, the software for these just felt completely separate.
They were. And OMTRA's philosophy is where they finally connect.
Yeah.
The core insight is that these tasks, they actually share a common informational structure.
What does that mean exactly?
They realize that if you break down a molecular system, it's really just a collection of different modalities.
Modalities.
Yeah, the fundamental properties. So you have continuous positions, the XYZ coordinates of an atom, and you have discrete identities, the atoms type, carbon, oxygen, nitrogen.
Oh, okay. That makes sense. So an atom isn't just a dot in space. It has a location, which is one kind of information, and it has an identity, like being a sulfur atom, which is another.
Precisely. And OMTRA is built to model both of those things at the same time in a unified way.
And that unified approach is what gives it its flexibility.
That's the magic. It starts to treat these totally different tasks as just different ways of partitioning information. If you're doing docking, the molecule's identity is fixed, right? That's your starting condition. You just generate the best position.
Okay.
But if you're doing de novo design, both the identity and the position are being generated from scratch. The underlying AI mechanics are almost identical.
It's just a question of what you hold constant and what you ask the model to create.
You got it.
And that's what lets OMTRA handle this whole spectrum of tasks. The sources list molecular docking, de novo design, even generating different 3D shapes for a known molecule.
And the really unique one, pharmacophore condition design. We'll get to that. It's where the human element comes in.
So we have this great philosophy. Treat position and identity as part of the same problem. But how does the AI actually do that without falling back on those old, slow search algorithms?
Right. That's where the cutting-edge math comes into play. OMTRA uses a technique called multi-modal flow matching. It's a type of transport-based generative model.
Flow matching. That sounds complicated. The sources suggest it's a really efficient way to generate data, though.
It is, yeah. Essentially, the model learns a smooth path or a flow between something really simple like random noise and the complex real-world data of what a correctly structured molecule looks like.
Okay.
The huge advantage is that once it learns this path, it can generate new molecules very quickly in a non-iterative way. It's much, much faster than older methods.
So it's like it's learned a shortcut to the right answer instead of searching the whole space every time.
That's a great way to put it. And what the researchers did was extend an already state-of-the-art model called FlowMol3. They adapted it to handle these really complex, heterogeneous graphs. So you can think about the ligand, the protein, and other things like cofactors all at once.
And I'm guessing to train something that sophisticated, you need a pretty massive data set.
Colossal is the word. And this is another major contribution from the paper. They created and open-sourced the Pharmit Dataset.
Which is
It's one of the largest collections of 3D molecules out there. Over 500 million 3D molecular conformers.
Wait, 500 million, is that just academic flexing? What does a data set that huge actually get you?
It seems like flexing, but it's absolutely necessary for the pre-training phase. The sources say this massive data set is essential for teaching the model on protein-free tasks.
Meaning what?
Meaning it lets the model just learn the fundamental rules of chemistry and geometry first. It builds a foundational knowledge of what molecules are supposed to look like, way beyond the specific examples you find in successful drug-protein pairs.
So it's building a general chemical intuition before it ever tries to solve the specific binding problem.
Exactly. It's a very broad education.
Okay, so the model is ambitious, the math is advanced, the data is huge. But in this field, none of that matters if it doesn't perform. Does OMTRA actually work better than what we already have?
It sets new records. I mean, it goes head-to-head with the big players, including AlphaFold 3
Wow, okay.
and highly optimized traditional methods like DINA, and it comes out on top.
Let's start with the novo design then, the invention part. The first thing you need is a molecule that's actually, plausible, chemically sound, not just junk.
Absolutely. The metric for that is often called PB-valid. OMTRA hits about 90%.
So 9 out of 10 molecules it invents are chemically sound. Let's just call that chemical integrity.
Good term. It excels at chemical integrity.
But the real goal isn't just a valid molecule, it's a molecule that works, one that actually binds correctly to the protein.
Precisely. And that's the combined metric. Chemical integrity plus interaction parity. And here, OMTRA produces successful ligands 37% more frequently than the next best method.
37% more?
Yep. We're talking a 26% success rate for OMTRA versus 19% for its closest competitor.
That's not just a small bump. In a drug discovery pipeline, that has to translate into a massive speed up, right?
It does. It means fewer wasted cycles on molecules that look good on paper but just don't bind. It speeds up that whole iteration process tremendously.
Okay, so what about docking, where the molecule is already known?
State-of-the-art performance there, too. On the Postbusters benchmark, which is a really tough test.
And the stats?
They're kind of astounding. So they let the model sample 40 possible poses. Then they look at its top-rank prediction. 91% of the time, that top-rank pose is both chemically plausible and highly accurate within 2 angstroms of the real structure.
Hold on. 91% top 1 accuracy? The sources compare that to AlphaFold 3 at 84%.
It is.
Isn't that the headline right there? Why even bother with de novo if the docking win is that huge?
That's a fair question. And it really gets back to OMTRA's whole philosophy. The docking win over a giant like AlphaFold 3 is a massive technological leap, no question. But docking is only one piece of the puzzle. The real gold, where you generate new intellectual property, is in the flexible de novo design. The fact that OMTRA does both at a state-of-the-art level in one framework, that's the breakthrough. It simplifies the entire toolchain.
I see. So it's the unified performance that matters, not just winning on one metric.
Exactly. Though, it's not perfect. The researchers noted a really interesting technical detail. Even with this amazing performance, some of the dock poses would fail because of issues with unconserved tetrahedral chirality.
Chirality. That's the handedness of a molecule, right? The left-hand versus right-hand version.
That's the one. It's crucial for biological activity. And to fix it, they had to go in and add an explicit penalty for getting the chirality wrong in the ranking algorithm.
So even with this cutting-edge AI, some fundamental chemistry rules still needed a manual override to get it right.
It proves you still need that explicit human enforcement on the back end.
Which leads us perfectly into what you called OMTRA's most innovative feature, its ability to actually incorporate that human knowledge up front.
Yes, the pharmacophore conditioning.
It's the only model that supports conditioning on both the protein pocket and user-supplied pharmacophores at the same time.
And this is a huge step toward making AI a true partner for researchers. A pharmacophore is, well, it's basically an abstract, human-interpretable guide.
A guide.
Yeah, a researcher can define desired molecular features like, I want an aromatic ring here, or I need a hydrogen bond donor at this exact 3D location.
So instead of just telling the AI, here's a pocket, find me a drug, the scientist can say, here's a pocket, and by the way, the drug must have a hydrogen bond donor right here and an aromatic ring over there.
Exactly. You're injecting years of medicinal chemistry knowledge directly into the design process. And the impact is, well, it's substantial.
The numbers in the sources really bear that out. For de novo design, the interaction recovery rate jumped by 10 percentage points. It went from about 51% to almost 61%.
A massive lift from just adding a few constraints. But the efficiency gains are what really blew me away. The researchers found that adding just 3 pharmacophores as guidance, it reduced the amount of computational sampling needed by 56%.
56%, just from 3 hints.
56%.
Wow. So that transforms it from a brute force search into a highly targeted discovery.
It really does. And it wasn't just for de novo. It also significantly improved the quality of the docked poses for known molecules. Interaction recovery went from about 80% to over 90%.
It just seems to confirm that explicit human guidance is a more powerful signal than just more number crunching.
It strongly implies it, yes. Which brings us to, I think, the most critical finding in the whole paper. A real paradox.
Which is?
The surprisingly modest results from all that massive scale pre-training.
Right, the 500 million molecules.
It's the elephant in the room. You have this massive engineering success, you dump this colossal data set into it, and the benefit was inconsistent. Sometimes it even made things worse.
Wait, what? So the human guidance provides this huge lift, but the sheer scale of the general data only gave a modest benefit.
It really challenges the current dogma that more data is always better. For instance, the pre-training did help with chemical integrity in de novo design, but for docking, it actually reduced the physical validity by 4 percentage points.
So training it on a giant general chemistry library made it slightly worse at the very specific task of docking.
A clear case where that general knowledge did not reliably transfer to a specialized task.
So weird.
And it gets weirder. The multitask training itself, the idea of training for docking and design at the same time, it also slightly impaired the de novo design while it was improving the docking.
Which raises a huge open question for the whole field, doesn't it?
A massive one.
Can these giant generalist AI models actually achieve meaningful transfer learning across different molecular tasks?
That's the question. I mean, despite this huge shift toward building these big unified models like OMTRA, the hard empirical evidence for consistent transfer learning, it's still pretty limited.
So the engineering is maybe a little bit ahead of the AI theory right now.
I think so. OMTRA is a huge engineering success because it can do it all. But the path to true AI generalization, the kind that really leverages scale, is, well, it's still complicated.
But its flexible architecture must be a fantastic test bed for trying to solve that problem.
Oh, absolutely. And the researchers pointed to the next big challenge they haven't even evaluated yet.
Which is?
Extending the model to generate the protein structure itself is another modality.
Alongside the ligand.
Alongside the ligand.
That would be the final frontier, because then you could design drugs for flexible proteins, or proteins where you don't even have a known structure.
It would move the whole field away from these static targets and toward the messy, dynamic reality of biology.
The ultimate vision, I guess. A single model that understands the entire drug-target interaction universe.
That's the dream.
What an illuminating dive. I mean, OMTRA's core contribution is just undeniable, isn't it? It achieves state-of-the-art performance in both de novo design and docking, all inside one framework.
It really proves you can combine these traditionally separate tasks into one powerful architecture.
And its ability to bring in user knowledge through those pharmacophores, that seems like the most immediate practical breakthrough. It improves efficiency and accuracy just by welcoming human insight into the loop.
I completely agree.
So we've seen this AI model hit top performance by integrating all these different modalities, position, identity, and crucially, explicit human knowledge. And yet, the benefit from the sheer scale of data, that 500 million conformer data set, and the multitask learning, well, that seems marginal for now, inconsistent.
Which leaves us with a really provocative thought to end on. We saw that strategically applied human knowledge gave a 56% efficiency boost, while the big data approach produced these inconsistent results. So as these generative models keep getting bigger and bigger, will that reliable transfer learning, the kind that justifies these giant data sets, will it eventually become the norm? Or will the greatest breakthroughs continue to come from the strategic, interpretable guidance provided by human expertise? It suggests that in this whole quest for the ultimate molecular AI, the human user might just be the most valuable signal of all.